Okay, let me go over the problems that were posted. So the conceptual problems, mostly interpreting graphs. So be careful about the graph that you're thinking about. So let me walk through these. So first one, so this is a position time graph. So position time graph. So when things cross on a position time graph, they're at the same position, right? So be careful about that. So here, Ariel and Byron, they are at the same place at the same time, twice in this curve. So second thing, remember what I'm gonna get off of here. So the slope off position time graph is gonna tell me velocity. So if I have a curve, right, my instantaneous velocity is going to be, right, the tangent line at that point. So if we're doing calculus, right, this is derivative, but really this is the tangent line. So I can find the slope. So notice I have a curve here. Any part of a smile is positive acceleration. Any part of a frown is negative acceleration. So here I have Ariel going at constant speed, and I have Byron that's experiencing positive acceleration. This is part of a smile. Do either children change direction, right? So the question is do they head back in the direction they came from? So no, I don't see that, right? So this always has positive velocity. So any tangent line I take along here is going to have a positive slope. So it's positive velocity. They're moving in the positive direction. And Ariel has positive slopes and positive velocity. So a good way to describe that is to talk about the slopes of the lines always being the same sign. So are the two children ever at the same position along the hallway? Yes. So twice they're at the same position at the same time. That's just being shown on the diagram here. Do the children ever have the same speed? So an interesting question. So if I look at the instantaneous velocity, it starts here, for Byron. So it starts here being less than Ariel, and it ends up being more than Ariel. So at some point in there, it's going to have exactly the same velocity. And it turns out if they're experiencing constant acceleration, it's going to be exactly halfway between here. So exactly halfway between here, wherever that is. So I'm going from seconds 2 to 9. So 3.5 seconds past this. So what's that, 5.5 seconds? So at 5.5 seconds, right here, if I was to draw a tangent line on this, I would find that tangent line is parallel to Ariel's line. So this is going to be meaning they have the same velocity. So there's one point on the graph where they have the same velocity. So this is also the average velocity between these 2 points. So if you have a curve like this undergoing constant acceleration between these 2 points, the average velocity is going to be the tangent line right in the middle. And as you can see for this straight line, right, that straight line is also, the slope of that straight line is representing the average velocity. For Ariel, the average velocity is constant, right? It's always the same. But for Byron, the velocity changes from lower to higher velocity, right? So the slope changes from smaller slope to higher slope. But the average velocity will be right in the middle of that time point. Again, experiencing constant acceleration, so it's different otherwise. Graph number 2. Let's see what we got here. So now I'm looking at velocity versus time. So I'm going to think about my 2 things. What does the slope tell me? The slope's going to tell me acceleration. And the area under the curve is going to tell me displacement. So I want to be careful about this. So when the points cross here, this means that at the same time they have the same velocity. They're not in the same place, but at the same point they have the same velocity. So they could be very far away from each other. Who knows? So headed twice, they have the same velocity. But okay, 2, either children change direction. So let me think about this. So here I'm not going to interpret the slope. I'm just going to interpret the velocity. So does the velocity change signs is another way of saying this. So here, Ariel, constant velocity, always positive. So she's not changing directions. Here, Byron starts out with very small velocity. Right? So I'm just reading this off the graph. I'm not taking the slopes. So I'm just reading off the graph. So it starts with small velocity, and that velocity increases, but is always positive, so he doesn't change direction either. Do the children ever have the same velocity? So yes. So who knows where they are, right? So the displacement is harder to figure out, but the same velocity. So these graphs cross at the 2 and 9 second point. So at those 2 points, they have the same velocity. So remember, on the displacement graph, we had to take the slope of the tangent line and compare the slopes to find velocity. Here's the velocity graph, so I'm just reading it directly from the graph. Do they have the same acceleration? Well, now I need to take my slopes, and same thing, I'm going to find here that the slope of this line, so I can make a tangent line somewhere in the middle here, and it will be parallel, meaning it's going to have the same slope. So there is a point in there that they have the same acceleration. So notice that Byron's acceleration, his rate of change of velocity, right? His tangent line is increasing as he goes along. But at one point right in the middle here, so this is between 2 and 9, so the half of that, half of 7 is 3.5. So I'm add 3.5 to 2. What do I get? 5.5. So at 5.5 seconds, right here, 5.5 seconds, that the tangent line will be, assuming this is a constant rate of acceleration. So, okay, that's helpful to be clear about the similar looking graphs, but when you plot displacement, it's completely different than when you plot velocity. So in the first one, the displacement graph, if I was to draw a displacement graph for this, right, what am I going to see? Well, I'm going to see that Ariel is getting steadily further away. So Ariel now is undergoing acceleration, so she's going to have some curve. And Byron is getting steadily further away at an increasing rate, so he's going to have some different curve. It's just going to be steeper, right? So it's really hard to interpret on a displacement graph. So this is going to be constant acceleration, and this would be like increasing acceleration. So really hard to tell on a displacement graph. For the most part, though, if it's a displacement graph, we'll assume it's constant acceleration. Changing y-axes. Okay, so let's see what's going on here. So they're not giving me a y-axis, but they're asking me to try different ones, I'm going to guess. So in one dimension of motion, so the vertical axis is not labeled. The vertical axis is position. Does it ever change direction? So if this is position, right, what happens, I start out with a negative slope, so as velocity, it comes to a stop, and then I get positive velocity after the 5-second mark. So does it change direction? Absolutely. So it's going in the negative direction, turns around and goes in the positive direction. And that's the 5-second point. So again, I'm going to worry about my tangent lines, and that 0 tangent line at 5-second points is going to be the point where it stops and turns around. If it's velocity, is it changing directions? Well, I don't know. So let me think about this, right? So I've got negative velocity, then becoming positive velocity. Huh. Yeah, so he's got to be changing directions. Right? So I have a positive velocity here, so I'm assuming this is 0 here, right? So now I'm reading from the graph here, this is positive velocity, and now this is negative velocity. Okay? So I start out with positive velocity, it decreases, right? So I'm going in the positive direction, but I'm slowing down. And I get to a point where I stop, right, at 0 velocity, and then I turn around, I have negative velocity, that increases, and I have a maximum negative velocity at 5 seconds. And then I slow down my negative acceleration, right? So the magnitude of my acceleration decreases till I get to 0 again, 0 velocity, and then I continue. So notice what's happening. My acceleration now is changing. So my acceleration starts out as negative, goes to 0, and then I start accelerating in the opposite direction. But my velocity is going to be 0 at 2 points. And that's where my velocity, again, this is being a velocity graph now. My velocity is going to be positive, become 0, so it must be changing directions, and then go the other way. So in this in position graph, I have a single change. If it's a velocity graph, I have 2 changes of direction. Okay, good one. Let's see, a couple more. Average speed. So let's see what we got here. Average speed. So this is each graph position is a function of time. So speed, so I'm going to rank the slopes of these. So speed is going to is really velocity, but it doesn't matter the direction. Right? So speed, your speedometer, your car doesn't know what direction it's heading. It just tells you how fast you're going. Right? So the speed, so this is going at, the slope of this is 0. So I'm going to say that's the worst you can get. This slope is going to be, what's that? I'm going to say that's 4 divided by 4, so this is going to be 0. This slope is going to be 1 meters per second. This is going to be 8 meters in 4 seconds, so this is going to be 2 meters per second. And this one is going to be 8 meters in 2 seconds, and then another 8 meters in 2 seconds. This is going to be 4 meters per second. So the average speed, dCBA. And when there are numbers, calculate it. So if they give you numbers, right, just calculate it and come up with an answer. That way you'll be confident about it. Distance traveled. So the velocity time graph, distance traveled, I'm going to look at the area under the curve. So here I have 1, 2, 3, 4, 5, 6 boxes. No, I guess we're 1, 2, 3, 4, 5 boxes underneath. So I'm going to call this a -5. And they're asking for distance traveled. So the fact is negative doesn't matter. If they're asking for displacement, I would worry about the negative sign, but distance traveled means it doesn't matter if it's positive or negative direction. Here I'm going to have 1, 2, 3, 4, 5 plus another 2 and maybe 7.5. 7.5 boxes altogether. Here I'm going to have this positive and the same amount negative, so that's going to add up to 0. Here I'm going to have 1, 2, call this 3, I don't know, and a half. And 1, 2, 3, I don't know, and a half, but negative. And here I'm going to have 1, 2, 3 and a 1, 2 and a half, we'll call it. So distance traveled, so the farthest one is D, second farthest is A. I don't care about negative signs. B and C are going to be equal, followed by F, and finally E. Ended up back at the same place. Anyway, hope that makes sense, and we'll talk to you later. Bye.